Good evening, students. My name is Shashank Shekhar, and we are doing a crash course on chemistry of 45 days for the upcoming JEE exam. And today is our 16th day. So, today we will be doing our second day of ionic equilibrium. So, the chapter which we are continuing is the ionic equilibrium. So, we have already covered the chemical equilibrium, and today is the last day for our equilibrium chapter. So, today's contents are mainly salt hydrolysis, buffer solution, and then we will solve some questions to do so. So, high respect, thank you for joining our lecture. So I will be using some abbreviations throughout the chapter. So if you are not aware about it, you can see them here. The first one is for strong acid, I will be using SA. Similarly, strong base SB, weak acid. Sorry, this one will be weak acid that will be WA, weak base that is WB, conjugate base that is CB, and conjugate acid that is CA. CA. Sorry. Sorry for this mistake. So this all will be the abbreviations I will be using throughout the lecture. So do not get confused. I would be saying that name also, but it is written as SA, WB, and all these things. So to understand buffer solution and hydrolysis, so children get confused at where to apply the salt hydrolysis and where to apply this buffer solution and where to not to apply any of these of two. So to do that, first of all, you should be aware about these two formulas that we have. The first one is about the if if we are reacting the same species, suppose we are reacting two acids and two bases. So if we are reacting two acids, then we will get H plus as M1V1 plus M2V2 by V1 plus V2. And if we are reacting base and base, that would be weak base, strong base, strong base, strong base, or anything, then it would be M1V1 plus M2V2 by V1 plus V2. Now, the second equation that we have here is, so if you are reacting to different species, that is different species, my like if you are reacting acid and base, by two different species I mean acid and base, then if the acid is present in large amount, then we will get H plus concentration as M1V1 minus M2V2 by V1 plus V2. So here M1V1 is greater than M2V2. So this is for acid. If in case if it is having more number of acid concentration or H plus concentration. Similarly, we do have this thing for OH minus if we have greater or basic nature of the solution. So it will be M1V1 minus M2V2 plus V1V2, in which case the concentration M1V1 will be greater and it will be for the concentration of hydroxyl ion. Now the main thing to notice here is that, so if you have to get this formula more clearly, then you must know that the concentration here, all the concentration we are talking about, that is M1, V1, M2, V2, are not of the acid or bases. It is of the H plus concentration that is given by that acid or base. So if we are considering a strong acid, a strong base, then H plus concentration simply will be the concentration of that acid or base. But if we are considering weak acid or weak base, then we do have to find the concentration of that acid or base. So those who do not know the formula, it is given as, so I have taught in the early class also. So we know that alpha is given by K by C. Therefore, the concentration of C alpha for monoprotic acid, it will be this one, where Ka is for acid and Kb is for base. So you will find the concentration of H plus ion or OH minus first of all, then you will use this formula. And V1 and V2 are their respective volumes. So suppose M1 is the concentration of having V1 volume and M2 is the concentration of V2 volume. So this is the formula. Now we have different kind of situations. So we will deal those cases one by one. So the first case is that M1V1 is equals to M2V2, by which I mean that all of the acid and all of the base have reacted and completely neutralized. Now four cases arise. The first one says that we have used a strong acid and a strong base. So in that case, there will be no hydrolysis. So keep this chart in mind. It will help you throughout the this chapter and make things more easier, because this chapter is very complicated as compared to chemical equilibrium. So if there is a complete neutralization, that means I mean that N1V1 is equals to N2V2. So in case of if it is having more than one, you can say n factor, and if it is having same n factor, then it is M1V1 equals to M2V2. So If we are having a strong acid and a strong base and we are completely neutralizing it, then there will be no hydrolysis. So we'll see what is hydrolysis in later chapter. Just remember this thing, that hydrolysis only for strong acid, weak base, weak acid, strong base, and weak acid or weak base. So you can see one thing common here, that for complete neutralization and hydrolysis to occur both at a time, you must have a weak thing. That can be a weak acid or a weak base, or both can be weak acid or weak base. In case of both are strong acid and strong base, there will be no hydrolysis. So this is the very starting point. Then we will also see what happens in case of incomplete neutralization, or we can say in where N1V1 is not equals to N2V2. So first we will see this one. So what is hydrolysis? So hydro means water. So basically the salt that is formed, it is reacting with water and has somehow and somehow changing the pH of this water. Now it can result in both acidic and basic solution depending upon the nature of salt that we have. Okay. So let us see how this hydrolysis happen. So suppose we have a reaction salt, which is so we know that salt is always present in dissociated form, because salt is a strong electrolyte, so it is 100% dissociated. I have told this thing earlier also. So suppose the salt we are considering is NH4Cl, which is a salt of NH4OH plus HCl, where NH4OH is a base and HCl is an acid. So we react these two to get our reaction, that is NH4Cl and H2O. So this is the reaction. So therefore we get this salt as NH4Cl. Now this HCl and NaOH have the same number of equivalents, that is N1V1 is equals to N2V2. Now we know that salt is present in dissociated form. Now what happens is that this salt we have, it reacts with water to give H plus. How? So this is the salt. So it is the cationic part of salt. So this is the weak base. You can say it is a conjugate acid of that base. So this NH4 plus reacts with H2O. Of course, this Cl minus will also react with H2O, but it will not result in any product. But in case of reaction of NH4 plus H2O, it gives us NH4OH. So which is the base that we have, that is the parent base of this NH4Cl, and plus H plus ion. Now we know that this NH4OH is a weak acid. Okay, so this is a weak acid, so it will not dissociate backward as much. It has formed in the forward direction, due to which the H plus concentration ion increase. So what do we see in hydrolysis is that this salt, the cationic part of salt in case of weak base, reacts with water or get hydrolyzed by water to form the weak base here, weak base plus H plus ion, and this resultant H plus ion decreases the pH or increases the H plus concentration of the solution. The same thing is written here, the resultant ammonia is a weak one. So it will not revert back, or it will not go in this direction as much as any other salt would have gone, or any strong acid or strong base would have gone. So in case of Cl minus, if it is, so Cl minus plus H2O would have given HCl plus OH minus. But we know very well that HCl is a dissociated form, so it will automatically and quickly revert back to this Cl minus and H2O, and we will not see any OH minus jump. But in case of NH4H, which is a weak base, it will not revert back easily, and we will get a jump in H plus ion. Okay. Now, I will not go into the detail of this. Say we have this derivation. We will just know the formula, because in exam we have to know the formula that to solve the question. So the first one is the hydrolysis constant. So hydrolysis constant is nothing but the equilibrium constant into water concentration for this acidic salt. So why it is acidic salt? Because it has increased H plus ion. So if you want to remember that which is one acidic and which one is basic, so the simple idea is that if you are using a strong acid and a weak base, so since remember that the acid is strong, so the salt will be acidic in nature. So you must have studied this concept in class 10th also, but do not know this mechanism, that how does it happen. So it is happening in this way. Now if we have to know the hydrolysis constant, it will be simply Kh is equals to Kw by Ka. What is Kw here? We know that Kw is the ionization constant for water, that is Kw, and K is the base ionization constant, that is Ka. Now the next one is the hydrolysis, degree of hydrolysis, which is calculated as root under Kh by C. Okay. So degree of hydrolysis of by mean that what fraction of this molecule we have undergoes hydrolysis. So it is as simple as that. So we have such, say we have NH4 plus in some amount, and out of those some of this goes to hydrolysis. So it is that fraction which goes into hydrolysis. The next one is the pH calculation. So we do have a simple and right straightforward formula for that, which is half pK plus log C. So this log C here is the concentration of, so it is the concentration of salt. So if you know the Ka of the acid which will be given in the question, take out the pK, that will be minus log K, and take the log C of it. So you know the formula for log C, so you know the formula for concentration. So if it is given, if the number of moles is given, simply divide by the volume, you can get the concentration, and you can calculate the pH from this. Now you can see one thing very clear here from the formula also, if you want to remember it, that it should be 7 minus. Why should be minus sign here? Because we know that we have having a acidic salt, and for acidic condition we should have a pH less than 7. So this formula goes as 7 minus half pK plus half log C. Okay. Now let us take the example of basic salt. So in basic salt we will take a strong base, and we know that the salt that is formed will also present as dissociated form. So suppose this is the salt we are taking. So if you want to know the parent this acid and base for it, it will be simply CH3COOH plus NaOH, which would give us CH3COO minus or Na plus and plus H2O. So this is the weak base we are having here, and this is the strong base, sorry, weak acid we are having here, and this is strong base we are having here, and this is the salt we are getting. Okay. Now what happen is that in the next part, this weak acid react with OH minus. So react with water to give OH minus. So it will be acetate ion reacting with H2O. Now it will again take this H plus to form this acetic acid, which will be not easily dissociated to the left reaction, or it will not be in the backward direction much more. Now due to this reason, this OH minus is released in this solution after hydrolysis of this acetate ion. Now due to this excess OH minus, the solution will be basic in nature. Okay. So the resultant acetic acid is a weak one, so it will not revert back, and we will result in excess OH minus ion. So same reason for that we are having for acidic. Now the formula are quite similar, only we have to replace that Kw by K, Ka by Kb, that would be Kw by Kb is equals to Kh, H is equals to root under Kh by C. So if you write it further, you can write it also as Kw by Kb into C. So it can be also the formula if you put the value of Kh from there. Now further, you can see very clearly here that the pH is greater than 7, as we are adding something to this pH, that is 7 plus half pK plus half log C. Again, the C that is written here is the concentration of salt. Okay. Now next, let us consider the fourth case we have. So first we have seen that strong acid and strong base complete neutralization. So it will give a neutral solution having a pH of 7. Then we have a strong acid and weak base. So since it is a strong acid, the solution will be acidic, that is the pH will be less than 7. Then we have a weak acid and a strong base. So if we are having a strong base, we will get a basic salt. Therefore the pH will be greater than 7. Now let us see the example of a weak acid and weak base. So again in this case also the salt will be present in dissociated form in water. So suppose we have this one as a salt. So what will be the parent acid and base? So it will be NH4OH, that is ammonium hydroxide, plus HCN. So both are a weak acid, so it is a weak acid and a weak base, and a complete neutralization gives us NH4CN plus H2O. So this is the salt we have here. Now further, both weak acid and weak base parts react with each with water. Now in this case, we have two things, that is NH4 and Cn minus, and this both will react with water. Okay, so this will be the reaction. So NH4 plus will react with this OH minus, it will give NH4OH, and Cn minus will react with HCN, which react with H plus and give HCN. Now in this case, we cannot see any H plus or OH minus that is released. Now it will all this all will depend upon the strength of the acid and bases, the relative strength of an acid and bases. Okay. So how we'll compare the strength? So we have this ionization constant value, that is K and Kb. So if K is greater than Kb, that means we are having a strong acid. Therefore, we will get an acidic salt. Similarly, if we are having a greater value of Kb for a weak acid and weak base salt hydrolysis, then we will get a basic salt. At the last, if K is equals to Kb, which is the last case, we will get a neutral salt again. So it is same as a strong acid and strong base, but if we are getting the same, you can say K and Kb value for a weak acid and weak base, we will get a neutral salt. So this is generally not a case. We cannot see any acid which has an absolute same value for K for any weak acid and weak base. So it will, you can say an ideal case. It can be mentioned in the question, then ask. Okay, so it is a hypothetical case, but question can be asked from here also. Okay, this we have some changes in the formula for this case. So if you want to find the hydrolysis constant, it will be Kw by K into Kb. So we have Kw by K for this acidic, then Kw by Kb for basic. We have Kw by K into Kb both for Kh. If you want to find the hydrolysis constant, the formula reduces to root under Kh, just root under Kh, and not by C. So the part of the final formula, it will be root under Kw by K into Kb. The formula for pH calculation is 7 plus half pK minus half pKb. You can see here very clearly that it is minus K and Kb. So if this whole value comes out to be greater than 0, or you can say positive value, then you will get this as 7 plus, that will be basic solution. So when it will happen? So in case of if pKb is less than pK. So you can see very clearly that what happens if K is greater than Kb. Okay. Now, we have seen the case of complete neutralization. Now we'll see what happens if we are taking an incomplete neutralization. So there are many cases arising in this case for this incomplete neutralization. So we'll deal it one by one. The first is the case is that we are taking a strong acid and strong base, and then we are having an incomplete neutralization, by which I mean that M1V1, for suppose we are saying for acid, so MaVa is not equals to MbVb, or if n factor is not 1, then it will be NaVa is not equals to NbVb. So for this case, the pH calculation is very simple. So whatever the amount of extra H plus ion concentration or OH minus concentration we will get after subtracting, that will be used to calculate the pH simply, that is minus log H plus or minus log OH minus or log OH minus, and we will get the pH in a very easy way. So that is the case for a strong acid and strong base. Now suppose we are getting a strong acid and a weak base. Now if H plus is left, by which I mean that H plus concentration is more, that is the strong acid concentration is more, in that case simple pH calculation is done. So in that case also, the extra H plus concentration we have, we will take the minus logarithm of that one and get our pH. But if we have extra OH minus, then a buffer solution will form. So here comes the idea of buffer. So if we take a strong acid and a weak base and we react with these two, and we know that the equivalence of this weak base is more, then we will get a buffer solution. That is what is the thing that will be remaining. So this both will react and we will get a salt, and since weak base is more, we will get some concentration of weak base remaining. This is not equation anymore. Do not consider the equation, consider as the product. The salt plus a weak base, we will get the remaining weak base. Okay. For that case, we call the solution as buffer. Now, if we take the second case, that is a weak acid and a strong base. So, if again, if the strong base is present in excess, you will simply do the pH calculation about the remaining OH minus. But if H plus is left, H plus concentration is left, then again a buffer solution is formed. Now, the fourth one is weak acid and weak base. So, it is also from the buffer solution. So, we will not look at it qualitatively. We will only consider the three cases up to here. Okay. Now, what is the buffer solution? So buffer solution is something that if we add a small amount of acid or base to the solution, it will not change the pH of the solution. So it is a kind of resistive to pH change. Now, buffer example is also available in our daily life. So in your stomach, we have a buffer solution so that we do not get an extra amount of acidity in our stomach, so that we can get it, so that we cannot get ill easily. The second one is that and also one kind of buffer is there in our blood, which is a of Na2CO3 and NaHCO3, so it helps in maintaining the pH of the blood also. So the buffer solution is there, and if there's only a slight change in that buffer, it can ultimately result in very crucial condition of the human being or any living substance. Okay, so which are having a blood. So buffer is a very important concept throughout our life also, for bio life also, and for chemical laboratory and all of those. Okay, so many reactions do happen at a specific pH, the enzyme catalysis also in our body, so they do react a they're very specific to the pH, and a slight change of the pH can abrupt this biological method, and so this buffer is present there everywhere in our daily life. Now, what is this of buffer solution consist of? So it consists of a weak base and its conjugate acid, or a weak acid and its conjugate base. So I have formulated this idea of conjugate acid and conjugate base earlier in the Bronsted delivery concept. So those who are not aware about it, you can see the previous lecture, you can refer for that. And the main equation that is used throughout this buffer thing is called the Henderson-Hasselbalch equation. So it is used to find the pH for all of this buffer solution. We will not go into the derivation of this buffer solution. We will simply use those formula to find our answer. Okay, so let us move to our concept of buffer solution. Suppose this is the case we are having. So the first one is we are having is that we are having a weak acid and its conjugate base. So we have seen that the four cases, that strong acid and strong base, they simply will calculate this and that and all of this. So if you consider the very basic, that is we are taking a weak acid and a strong base, and the weak acid are present in excess, so due to which we get a result of the solution having a weak acid and its conjugate base. Okay, so let us start with this thing, the phenomena, how does it happen. Now we have this weak acid and its salt. So this is the weak acid, that is CH3COH, and its salt, that is acetate ion. So it can be present in any ionic form. It can be sodium acetate ion or potassium acetate ion. It can be anything. Now what happened when we try to change the pH of the solution so it is a buffer solution, of course. So it is an acidic buffer solution, because which acid we are taking, or which acid we are taking as weak, that will be the nomenclature of that buffer solution, for which, say, suppose we are taking acetic acid as the weak acid, which is acetic acid, so it will be an acidic buffer. Now what will happen is that if we add a small amount of H plus to this solution, we know that CH3CO minus and Na plus are present as in the form of salt. Now this H plus that we are added, that hydrogen ion we are added, it reacts with this acetate ion to give this CH3COH. Now we know very clearly that this reaction in backward is not that much feasible because of this strong dissociation constant of Ka. We know that alpha is less for CH3COH, means it did not dissociate very easily, but it forms in the further direction. Now due to what is the phenomena that is seen here, that we have added H plus ion, of course, but it is taken up by the acetate ion, and it is not reverted back in the backward direction because of the low ionization constant of this acetic acid, or low degree of ionization for this acetic acid. Now in this way, although we added this H plus ion, the pH of the solution has been not decreased. So this is the phenomena that is happening for can say on addition of H plus for an acidic buffer. Now suppose we add OH minus ion. So what will happen is that this OH minus will react with this acetic acid to form CH3COO minus and H2O. Okay. So this will form. Now you can see very clearly here that we are getting a CH3O minus. Okay, so this CH3OO minus we have got, it will all on present in the form of this salt, and we can see that the OH minus that we have added is being consumed completely. So since it is consumed completely by this acetic acid, we will not see any change in the pH on addition of OH minus. So in this way, you can say a weak acid and its conjugate base is helping in controlling the pH of the given solution, and they act as a buffer for the solution. So this buffer word is mainly used in the means in daily life also. So it is a kind of, you can say, relaxation that ones get in case of anything. So it can be a buffer days also. Suppose you're preparing for exam and you have some amount of buffer days, by which we mean that we have some extra amount of day for our preparation. In similar way, the buffer solution means if we add some H plus or OH minus, we have some relaxation in that there will be no change in the pH of the solution, although we have added some acid and base. And this is the action of this buffer solution. So how does this buffer solution control this? Now, similarly, we do have a basic buffer solution. So the mechanism is quite simple and it's quite similar to the acidic buffer. So how does it take place? So suppose we have this thing that is the NH4 plus and NH4OH. So this is the base we have and its corresponding salt we have here. So suppose we have NH4Cl here. Okay, so this is NH4Cl also. So it can be any cationic anionic part. We do not have to worry about it. Now we have added H plus to this. Now the same thing happens is that now H plus, since it is a base, it will react with the acid. It will give NH4 plus and H2O. We can see here again this H plus that we have added extra is been consumed by this NH4OH, and we do not see any change in H plus concentration. Okay. Therefore, the pH of the solution is changed by no amount, or you can say a very small amount. If it is also visible, then it is changed by a very small amount. Now, if we add an OH minus, it is now consumed by this species, that is NH4 plus, and we will get a NH4OH. Now this, we will get a NH4OH. Okay, and in this way, OH minus is consumed because it will not revert back in the backward direction. Now let us look it in the formula. So this is the important formula for calculation of this pH. So it is derived using Henderson-Hasselbalch equation. So we will not get into derivation as it is not important for the exams. So we do have this formula here. Okay, so if we calculate a pH for a acidic buffer, it will be simply pKa plus log conjugate acid by base, or you can also say log salt by base. So it is a concentration of salt we have, and the remaining base that we are having after neutralization. Similarly, we do have this for this case. Okay, so for basic buffer, it will be the concentration of acid divided by conjugate base, and it will be again pKb. Sorry for the wrong formula. Okay, the formula is quite you can say it is quite similar to this, only we have to replace this base by acid, and all other things are same. So it will be simply, if you write it in another way, you can also write such concentration of salt we have divided by concentration of acid. We again have the pKb in place of pKa. Now you can use this formula and find your answer. Now there is a thing called buffer capacity. So it is nothing but, you can say, It is a kind of strength measuring thing of buffer solution, that how much amount of H plus ion or OH minus ion it can take up and still maintain the pH of this solution. So it is a resistance that is means opposed, the resistance that is put upon to the upcoming H plus and OH minus, so that it can not change the pH of the solution that we have the buffer solution. Okay, so suppose it is denoted by this word beta, and it is calculated is change in concentration of base, means the amount of acid or base we have added divided by the change in pH that we are seeing. So there, if there is a change in pH and upon some addition of acid and base, then we can take that fraction and calculate the buffer capacity, that is beta. Okay. Okay, now let us move to some of the questions. So I put some questions here so you can get a more clear grasp of this chapter. So what does this question say is, we are having 1 m NH4OH and we are having 1 m and 1 molar HCl, and we are mixing to make a total volume of this 300 ml. And if the pH of the mixture is 9.26, okay, what is the pKa? So this is the pK given, what is the volume of NH4OH that we are having. Okay, so let us see how we will solve it. So I put up a solution here, very clear. I will explain it to you. Now the first thing we can see here is that we are having a pH of 9.26. So what does this mean? It is a basic kind of solution, that is NH4OH is present in a greater amount. Okay, so the concentration of NH4OH is greater. Okay. Now, if the concentration of NH4OH is greater, that we are taking HCl in smaller amount. Now we have seen that we have 300 ml of this solution. So let the HCl concentration be x millimole, or x millimole amount of HCl is present, or you can say we are dissolving x ml of this HCl. Now what will be the amount of NH4OH that we will have? So if the total volume is 300, then the volume of NH4OH will be 300 minus x, that is minus of HCl, and that much amount of millimole of this NH4OH we will have. So why we are not considering the volume here? So we can write the volume also because if you have to convert this ml into millimole, then we have to divide it into something. But we are not doing it so, because we already know that V1 is same, so do not get confused with it. Okay. And we also know that it is a 1 molar solution, so one of it will contain one of it, and one of it will contain one of it. So it is 1-to-1 relation. Now what we will do next is that, now since HCl is reacting with NH4OH whole, this X will be wholly consumed with NH4OH. So the amount of NH4Cl will form this X. Why? We know that the equation is of NH4OH reacting with HCl as NH4Cl plus OH. So if X amount of this have reacted with 300 minus X of this, so we'll get as X of this. Okay, so at equilibrium, all of these have reacted, and 1 mole will react with 1 mole, so 300 minus X will be reduced from this, and we will get a X of NH4Cl. So X millimole of NH4Cl. Similarly, what is the concentration of NH4OH that is left? So I have said it earlier also here. So it will be 300 minus X, that will be 300 minus 2X. Now we see here is that it is a kind of you can say that it is a kind of buffer solution, because we are having amount of salt and some amount of you can say a weak acid that is unreacted. So we are having a weak acid and its conjugate base, so it is a buffer solution. We know the formula for it very well. So it is POH is equals to PKB log NH4 plus by NH4OH. So we'll put those things here. So for those who don't know about POH, Okay, so this is the formula here. So 14 minus 9.26, that is 4.74. Okay, so this is 4.74. It also 4.74. So if we solve this, we will get it as this much. Okay, so if we revert this, we will get this much. Put the values all here. You will get the value of X as 100 ml. Now what is the volume of NH4OH? So if we know that it is 100 minus X, that is 200, and hence the volume of NH4Cl and OH will be 2 is to 1. Why? Because what was the volume of HCl? It was X mole, so X is equals to 100. So 200 by 100, that would be 2 is to 1. So this is the ratio we have here. This is the answer. Now next question is that we are taking a 2.5 ml of 2 by 5 weak monoacidic base is titrated with a 2.15 m HCl in water. The concentration of H plus at equivalence point. Now, those who are not aware about this titration, in titration we do that. The thing is that we take the same equivalence of acid or base that we are titrating with with the same equivalence of acid and base. Means the equivalence of both acid and base are same. That means N1V1 is equals to N2V2. Now since here NF is same for both of this, as we are taking a weak monoacidic and monobasic, therefore we will add our NF value as 1. Okay, because this is a monoacidic that is having a 1 OH and HCl is having a 1 H plus, so NF is same for both of them. So this is the case. So we know that N1V1 is equals to N2V2 for titration to be completed. Now we are reacting a base which is weaker, because we have get a value of Ka. It is very clear that we are taking a weak base and we are taking a strong acid and we are doing a complete neutralization of that. For that case, we will get a hydrolysis. So we will get a salt hydrolysis. And what kind of salt we will have? We will have a acidic salt. Now if you want to find the concentration of this of V2, so since N1V1 is equals to N2V2, it will be simply N1V1 into N2V2. It was 2.5 by 2 by 5 of M. It's 2 by 15 into V2. So we'll get it as 7.5 ml. Okay. Now suppose we take a hypothetical reaction, or you can say a known reaction also we can take, in which both of this are having, so this is already given, so it is having a monoacidic kind of base. Okay. Now 2.5 ml of 2 by 5 m base contain base is that 1 millimole. So how many moles of this will we have? Or in 2.5, how many moles will be present? Because we know that molarity is nothing but number of moles by volume. So if we multiply it by volume, we will get a number of moles. So since it is milliliter, we will get in millimoles. Okay. Now next. Now salt of BCl that is formed. So what is the salt of BCl that will be formed? So it will be 1 millimole. Why? Because we are doing a complete neutralization of this. So the amount of this that is reacting will the amount of salt we are having. So 1 millimole that we are having. And what is the volume of solution? So we are reacting 2.5 and 7.5 milliliter of the solution. We have calculated the 7.5 as well. So the total volume would be 10 ml. Okay, it will be 10 ml. Now next, what is the concentration of BCl? So it is the amount we have calculated, it is 1, and 1 by 1 millimole by 10 milliliter, it will be 0.1 m solution. Now for a salt of weak base and a strong acid, so it is an acidic salt, so we will have a pH that is 7 minus of this thing. Now since you have to calculate this, not this H plus pH, we have to calculate the H plus, we can use this formula also. It is nothing but just the formulation of the formula that we have used. It was pH is equals to half 7 minus half log C half log pKb. So if you look at this formula, it is same as that. If you take the log of it and all of this, you will get this formula. Also, you can this formula also to find the H plus concentration directly. So at this temperature, we know that Kw value is 10 to the power minus 14. Concentration is 0.1 if you calculated here. And Kb is given in the question. So it will be this one. Okay. So this is the solution of this. Okay. Now let us move to the next question. So what will the pH of buffer solution? So it is already given. We are having buffer solution prepared by mixing 30 gram of Na2CO3 in 500 ml of an aqueous solution containing 150 ml of MHCl. Now we are reacting a base, or you can say a weaker base, into a stronger acid, and it is already given that is a buffer solution. And since the weaker one is the base, so it will form a basic buffer. So how we will do this question? So first of all, you will calculate the number of moles of Na2CO3. So it will be simply 30 by 106 into 1000. And since we are taking a 1m solution of HCl, so the number of moles of HCl will be 150 into 1. And it will be into 1000. Why of 1000? Because we are taking a 500 ml of this thing. Okay. Now next, it will be 283. This value will be 283. And it is 150. So this is the number of moles we have. Okay. Now this 150 is present in smaller amounts, so it will react wholly with this. So 283 minus 150, we will get it as 133, and the amount of salt that will be formed, it will equal to 150. Why? Because 1 mole of HCl give 1 mole of NaCl. Similarly, 150 of this will give 150 of NaCl. It is simple unitary method. Now the solution we have here is that we have the number of moles of NaCl, we have the number of moles of this Na2CO3, that is the base. So it is a base and its conjugate acid, or base, weak base and its conjugate salt. Now it is a buffer solution, and of course a basic buffer solution. Now we know the formula for it. So it is simply pK is equals to our log concentration of CO3 2 minus by HCO3, and this is the 133 by 150. So we got it 133, we go 150. So we'll do the calculation and get it as 10.97. So this is the formula for this. Okay. Now let us move to our next question. So this question I have showed you earlier also, but since we have not completed the hydrolysis part, so we have jumped this question earlier. So today we will do this. So what does this question says is that the hydroxyl concentration in the case of sodium can be expressed K, and we have C, and of course we know Kw. So Kw is not given here, so let me write it here. So we have also Kw, and we have to express this 3 using 3 the OH minus concentration. So we know the formula very well. We will just rearrange that formula, that POH is equals to half pKb plus log salt by base. Okay, simply we will use this formula. So if you want to, you can rearrange it, take the anti-log on both sides, and you can use this formula to get upon this formula. So you can see the solution, it is given here also. So it is the thing, it is Cx root under Kb. This is the thing we are having, it is OH minus equals to Cs Kw Kb. So it is done in a different way. So we get the derivation is written here. Do not need to do the derivation. You can use the formula that we have of POH, the Henderson-Hasselbalch equation, and then you can take the anti-log and solve the formula to get our answer. Okay. So the next thing question we have here is that what would be the pH of a solution obtained by mixing 5 gram of acetic acid and 7.5 gram of sodium acetate. Okay, making the volume equal to 500 milliliter. So it is a very simple and clear cut question. pK is also given, K is also given. You do not have to do anything to solve this question. It is much easier question than the previous ones. So I have put this question here so you can get a start of this. So first we will calculate, we will simply calculate this concentration of H plus. So the mass we have given, we will divide the molar mass, and the total volume was add up to 500 ml. So we will convert it into liter, we will divide 1000, it will go outside. and we will get this at 0.166. Similarly, for CH3COAN, you can do the same method, divide it by this, divide by the volume or the in liter. That now we know the formula for buffer solution. So what is the formula for buffer solution? We know the formula, it is pH is equals to pK plus log concentration of salt, that is sodium acetate, divided by concentration of acid. Okay. So sorry, it will not be here, it will be only pK. That would be 4.76 plus log 0.183 by 0.166. So we will get this, and this will be the answer of our required choice. Now I have solved 5 questions. I will now show you some questions one by one. So I will give you a little hint of it also if you want, and then you can solve it by yourself to get a complete gesture of this ionic equilibrium. So it is not that tough chapter. You have just to follow the flow chart that I follow. So first of all, we have a case of two cases we have. So we will see the equivalence of both of this. So if both of these have the same equivalent, that is N1V1 is equals to N2V2, or in case of n factor is equals to 1, M1V1 is equals to M2V2, then we will have four cases: strong acid, strong base; weak acid, weak base; strong acid, weak base; and strong base and weak acid. Now in case of strong acid and strong base, we will have a complete neutralization and we will get a neutral solution. Why? So I am not shown the reason behind it. If you want, I can show you. So it is like this. So suppose we are taking a strong base acid, that is HCl, and a strong base, that is NOH, and we are reacting both of this. We will get as NaCl plus H2O. Now what is the salt that we are getting? That is NaCl. So it will dissociate completely. Why? Because it is a strong electrolyte. Now this Na plus, suppose it undergoes hydrolysis, it reacts with water. So what it will form? It will form NaOH plus H plus Ion. Now if you look at this formula, it is quite simple that this NaOH is a strong electrolyte. Why? Because it is a strong acid, a strong base. Now it will again quickly dissociate into Na plus and OH minus. Means we get this thing back, Na plus, and OH minus that we get will react with OH plus, sorry, H plus, and we will get this H2O back. You can see here clearly that a hydrolysis of Na plus does not have any net effect. It we get back the initial reaction that we have. Now similarly, if we do this for Cl minus, it will react with H2O, then we will get HCl and OH minus. Okay, and OH minus. Now again it will revert back, it will get H plus and Cl minus. This Cl minus will react with OH, will get H2O back. So we are getting each and every constituent of that we formed of using NaCl, that Na plus and Cl minus back. So we are getting Na plus back, we are getting Cl minus back, we are getting H2O back. So there is a no net change of H plus or OH minus, or there is no kind of hydrolysis for a strong acid and a strong base. For that reason, we do not consider any hydrolysis of these two species. Now the second case we have is a strong acid and weak base. So in that case, since we are using a strong acid, so whichever is the strong, that will for the nature of the salt. So strong acid means acidic salt, that will be pH greater than less than 7. Now if a strong base, then we will get a basic salt, so pH will be greater than 7. Now weak acid and weak base, so it can vary depending upon the ionization constant of the acid or base. So if the ionization constant or K is greater, then we will get a acidic salt, and if Kb is greater, we will get a basic salt. And if suppose we have a hypothetical case where both weak acid and weak base have the same K and Kb, then we will get a neutral solution. So that does not happen in real life. Now if we move to the incomplete neutralization, so if in any of the four cases, if that incomplete neutralization results in the residual amount of a weak acid or weak base. So if we have residual amount of a strong acid or strong base or any of these two, we will simply calculate pH by the remaining H plus OH minus concentration we have. But if we have any amount of this H plus and OH minus that is remained from the strong acid, weak acid or weak base, then we will have a buffer solution. So we have the two Henselberg equation. So that is pH is equals to pKa plus log salt by acid, that is for acidic salt, and POH is equals to pKb plus log salt by base, that is for basic salt. Sorry, basic buffer and acidic buffer. Sorry. So this was overall flow chart for calculating and all of this. So this will be used to and fro. You can use to and fro and solve each and every question we have in ionic equilibrium. So this was the overall concept. Now if you want, you can take screenshots of this question one by one. So it says that the pK of a weak acid is given, pOH of an aqueous buffer of HA in which 50% of the acid ionized is. This is the question. You have your whole options. You can take a screenshot. Now similarly, we have this question here. Okay, so I will wait for 1 minute. Okay. Now next. So I have also put out the question from the previous lecture, that is, it is of solubility product. You have to solve this also. So those who do not remember it, it is quite easy. It is given that your 10 to the power minus 3 HeMn2 plus, it is treated with 10 to the power minus sulfide. So it is a question of common ion effect. So we'll use this formula in which a solubility will be added of some amount of H2 plus. So to do it by yourself, you can do it. Very easy to solve if you know the concept very well. Okay, sorry. Here this thing is totally as pH. So pH is written here, nothing new is here. Okay, pH of the neutralization point of 0.1. So today this was for all of the today for this lecture. So tomorrow, the next chapter that we will dealing with is redox reaction. So it will be of 1 day. So get ready with it. Okay. So thank you for today's coming to today's lecture.